I will talk about AutoV, an automotive testbed for real-time virtualization. This is work done in Precise Center. As we know, automotive systems are becoming more and more complex. There are hundreds of tasks running on dozens of processors. These tasks need high performance and strong isolation. The tasks should not interfere with each other in terms of the timing properties. Multicore virtualization can help handle such complexity. For example, we can consolidate the legacy systems into virtual machines on a more powerful multi-core processor. Because the processor is more powerful, we can consolidate more systems into the same processor. This can help reduce the size, weight, and power consumption. And also because the processor is more powerful, the tasks in each system can have better performance. However, the multi-core virtualization also introduced new challenges. The interference on multi-core processor can affect the timing isolation. When we have multiple tasks running in multiple virtual machines on shared multi-core platform, the tasks inside the same VM can interfere with each other. The tasks in different VMs can also interfere with each other. If we look into the shared multi-core platform, we will find that there are many hardware components shared by the softwares, and these shared components are the source of interference. Real-time virtualization aims to achieve the timing isolation by eliminating the interference introduced by the shared component. One representative work is RT-Xen, which is short for real-time Xen, proposed by us and Washington University in St. Louis. The current RT-Xen have eliminated the interference caused by the CPU resource and shared cache resource. It also provides the analysis to analyze the interference introduced by the private cache resource. So this is the real-time virtualization. We ask the question, this is the real-time virtualization. In the paper, we did the evaluation based on the benchmarks. However, there's a gap between the benchmarks and the real automotive systems. So we ask the question, does real-time virtualization provide the timing isolation needed for automotive systems? In order to answer this question, we need to know how to evaluate the real-time virtualization for automotive systems. The current status is that our real-time community has real-time virtualization, but we have no access to the real automotive platforms or real automotive applications. In order to evaluate the real-time virtualization for automotive systems, we need to bridge this gap. That's why we propose AutoV. AutoV is an automotive testbed for real-time virtualization. It can help evaluate the timing isolation provided by the real-time virtualization for automotive systems. It consists of two parts: an automotive racing car, which provides the automotive applications as the evaluation workload, the RT-Xen, which provides the state-of-the-art timing isolation mechanisms for virtualization. In the rest of the talk, I will first introduce the autonomous racing car and RT-Xen before I introduce AutoV. And then I will show the evaluation with the AutoV for the real-time virtualization. The autonomous racing car comes from the F110 racing car developed by our group. This racing car can run in an indoor hallway based on a map. All of these operations are done autonomously. This car has three modes. In the first mode, the car will drive straight with a PD controller. When it gets close to the corner, it will enter into the brake mode. It uses the idea of the anti-lock braking systems, which is widely used in the current commercial cars. It brake and release the wheels frequently so that it prevents the car from sliding. Once the car's speed reaches to the specified speed, the car will come into turning mode. It will start to detect the corner and apply a constant steering angle until it gets out of the corner. Once it gets out of the corner, it will come into the fast mode again and repeat. So this is the high level functionality of the car. To give you a better understanding of what this car can do, let's have a look at the video that was captured in the racing competition last October. This car won the first place in the racing competition. Its average speed is 8.7 miles per hour and top speed is about 16 miles per hour. In the left corner, you will see the map the car follows. So this is the team. So this is our team that built this car. We have 4 PhD students from our group and 1 visiting student from Korea. Now we have seen the functionality of the car. Let's have a look at the architecture. The car is built on a remote control car. We mount the embodied board and LiDAR onto this car. The embodied board we use for the computation is the NVIDIA Jetson board. On this board, we run Linux and ROS. ROS is short for Robotic Operating Systems, which is a middleware widely used in robotic community. It provides a pub-sub networking and communication framework. On the ROS, we built the racing application. Each node is a process that have a functionality. And each node will be initialized as a Linux process scheduled by the Linux scheduler. The most important node here is the control node, which do all of the computation and control the steering of the car. So this is the architecture of the car. Now let's have a look at RT-Xen. RT-Xen provides 2 real-time functionalities. One is real-time CPU scheduling, which aims to eliminate interference from the CPU resource. And the other is the dynamic shared cache management framework, which provides the strong isolation in last level cache for the task in different VMs. It also enables the dynamic cache management for tasks in VMs. Due to time constraints, we will only focus on the real-time CPU scheduling in this talk. Before we talk about the real-time CPU scheduling, let's look at the Xen scheduler. In a Xen environment, the VMs run on vCPUs, which are scheduled by the Xen scheduler on multiple physical CPUs. The default Xen scheduler is called credit scheduler. It uses the round-robin scheduling algorithm with proportional share, which means that the CPU results a vCPU gets depends on the other vCPUs running in the system. The more vCPUs running in the system, the less results a vCPU will get. This means it has no real-time guarantees for vCPUs. In order to provide the real-time performance for the vCPUs, RT-Xen investigate a set of real-time schedulers. We started the early Stellar scheduling algorithm and rate monotonic scheduling algorithm that is widely used in the real-time community. We also started the global and partition scheduling model. Based on the evaluation in our paper, we conclude that the global EDF dominates the other scheduling algorithms in the empirical evaluations. So we upstream the global EDF in Xen as the RT-DS scheduler in 2015. We are currently actively maintaining the RT-DS scheduler. We rewrote the scheduler for Xen 4.7. We changed the scheduling model from the time-driven scheduling model to the event-driven scheduling model so that the scheduler can incur less scheduling overhead. Now let's have a look at the RT-DS scheduler. Under the scheduler, each vCPU is specified as two parameters, the period and budget. In this example, the vCPU will have 4 time unit as the budget and 10 time unit as the period. The vCPU will get its budget time at the beginning of every period, and its budget will decrease when a task runs on it. When there's no task run on this vCPU, its budget will not decrease. We may have multiple vCPUs running in the systems. The scheduler schedules the vCPUs based on their priority. The vCPU with earlier deadline has higher priority. The scheduler put all of the vCPUs with budget into the ready queue and sort them based on their priority. Whenever the scheduler is invoked, it will fetch the vCPUs from the top of the run queue and put it onto the cores. So this guarantees that at any time, the vCPUs running on the current cores are always the vCPUs with highest priority. When a vCPU runs out of its budget, it will be put into the depleted queue, which is sorted by the next release time. And because a vCPU's budget will be replenished in the next period. So when a vCPU has its budget again, it will be moved from the depleted queue to the run queue and get involved in the scheduling. So this is the RT-DS scheduler. Now we have seen the autonomous racing car and the RT-Xen. We will integrate them together to get the AutoV. We still have the same hardware. We still use the NVIDIA Jetson board as the embedded board. On top of this board, we run RT-Xen, which supports multiple vCPUs. Which support multiple VMs. In one VM, we run the autonomous racing car application. And in another VM, we run the non-real-time tasks. We put all of the raw service and drivers into the VM0. In order to have these systems, there are two things to do. First, RT-Xen cannot run on this NVIDIA Jetson board out of box. This is because the board has a special generic interrupt controller which cannot be handled by Xen or RT-Xen. So we need to bypass this interrupt controller in order to boot the system on this board. The second thing is that the VMs, such as the VM1 or VM2, has no access to the physical devices in the virtualization environment. In order to access the physical device, we need to run the device drivers into the special VM, which is the VM0 here. So this is the architecture of the racing car on RT-Xen. We evaluate the RT-Xen with the autonomous racing car. We want to answer 3 questions. Can the safety-critical automotive applications run in virtualization environment? Can the interference hurt the safety of the automotive applications? And can RT-Xen eliminate interference and guarantee the safety? In order to answer these 3 questions, we set up the following experiment. We pick a subset of the functionality of the car and let the car drive straight in a straight hallway for 5 seconds and then brake to stop at the end of the hallway. There are 2 types of workload. One is the racing car application. The other is the interference tasks. The interference task is the CPU-intensive task in this experiment. In the future, we will also consider the other type of interference. We create 2 scenarios. The solo scenario when only the racing car application runs, and the interference scenario when both the racing application and the interference tasks run. We have 2 types of environments for each of the scenarios. The Linux environment when the Linux run on the hardware directly. The virtualization environment when the Linux run inside the virtual machines on top of Xen or RT-Xen. When it runs on Xen, it uses the credit scheduler. When it runs on RT-Xen, it uses the Xen with RTDS scheduler. So we have 6 experiments to do. Let's first look at the Linux environment for these 2 scenarios. We will first have a look at the solo scenario, which provides the baseline for the rest of the experiment. It tells us the expected behavior of the car. As you can see, this car drives straight and brake stop at the end of the hallway. Now let's look at the interference scenario. Because when the interference task starts to run, it will consume most of the CPU resource and prevent the control task from running. When the control task cannot produce the control output quickly enough, the car will drift to left and crash. So we have seen that the interference could jeopardize the safety of the car. Now let's have a look at the RT-Xen environment to see if the autonomous racing car can run in the virtualization environment and can the RT-Xen handle such interference. Instead of showing the results for each scenario one by one, let's have a look at both scenarios at the same time and guess which one is the scenario with interference tasks.
It's just a Great. Okay. Great.
So can you guess which scenario is the scenario with interference task? It's hard to tell because the car has the exact same behavior. This is because the RTDS scheduler guarantees the CPU resource allocated for the vCPU that runs the control application. So we have seen that autonomous racing car can run in the virtualization environment, and the real-time scheduler can provide the required real-time performance for the racing application. We also did the experiment for the Xen credit scheduler, showing that the credit scheduler cannot handle such interference scenarios. You can find the video in our website, which will be shown in the end of this talk. So we answer the 3 questions we have at the beginning of the evaluation. To conclude, we propose AutoV, an automotive testbed for real-time virtualization. The evaluation demonstrates that automotive systems integration requires a timing isolation, and real-time virtualization is a promising technique to achieve such timing isolation. There are several challenges for us to investigate in the future. For example, how much evaluation should be done to claim the real-time virtualization can be used for automotive systems? And how to manage the other type of resources, such as the network and device I/O requests. As a future work, we plan to evaluate the other mechanism of RT-Xen, such as the dynamic cache management with the AutoV platform. We also want to make it available to others so that our community can develop more complex applications. So this work is done with a lot of collaborators. The autonomous racing car is done in our lab with 3 other PhD students and 1 master student. The RT-Xen project is collaborated with the Washington University in St. Louis. The AutoV is collaborative with 2 other master students. You can check out the rest of the videos and the source code later in our website. Thank you very much. If you have any question, please feel free to send an email to me.